Now that we know how to identify if a covalent bond is polar or not using electronegativities, we can now look at molecules that contain covalent bonds and determine if the molecule is polar or not. Okay, and honestly, the main thing here is if there's polar bonds or not, and the overall geometry of the molecules. So we learned both pieces this chapter. All right, so the question is now if a whole molecule is polar or not. And you would think, well, if the molecule has polar bonds, it's polar, and if it doesn't have polar bonds, it's not polar. And it's not quite that easy. You can have polar bonds and not be polar, and we'll see how that works in a second. So we'll start off easy. So we're going to look at initially diatomic molecules, and then we'll go to molecules that contain more than 2 atoms. So diatomic means molecules that only have 2 atoms, like we've seen, HF or Cl, Cl, or whatever. Okay, molecules that contain 2 atoms and they're covalently bonded together. Those molecules are polar if the bond is polar. Okay, this makes sense because there's only 2 atoms. So if we look at the bond and it's polar, then that molecule that contains only those 2 atoms is polar. Now, if we have molecules that contain more than 2 atoms, we're going to have to look a little deeper. Okay, so we're first going to discuss nonpolar molecules, molecules that overall are not polar. The first way a molecule can be nonpolar is if all the bonds are not polar. Right, so looking at this octane molecule, that's all carbons and hydrogens. It's called a hydrocarbon because it only contains carbons and hydrogens. That octane molecule is not polar. All the bonds, there's only 2 types. There's a carbon-hydrogen bonds and there's carbon-carbon bonds. Carbon-carbon bonds aren't polar clearly because they're both the same atom with both the same electronegativities. Carbon-hydrogen bonds we saw earlier were not polar because the electronegativity difference is not big enough to make them polar. So overall, octane is not polar. Okay, so all the bonds aren't polar, so the molecule is not polar. The second way this happens is all the bonds in the molecule are polar, and the central atom has no non-bonding electrons. So let's think about that for a minute. So we have polar bonds, but the central atom only has bonding groups, no non-bonding groups. So that means the bonding groups are equally separated around that central atom, right? Like we saw CO2, where it's linear, but one bond goes this way and one bond goes this way. Or if we have trigonoplanar, that means we have electron groups at, equally spaced around the circle. It's a triangle. Or tetrahedral, where the 4 electron groups, in this case there would be 4 bonds, are equally spaced around the central atom. So if we have all the bonds being polar and they're equal, they're the same bond, so they occur between the central atom and the same other atom, what happens is the dipoles cancel out. So we're going to see that right here. So carbon dioxide contains polar bonds. The carbon and oxygen bonds, each one is polar. The oxygen is more electronegative than the carbon. So therefore it's a polar bond, except both carbon-oxygen bonds are polar. And one has a dipole going this way, and one has a dipole going this way. And when we deal with dipoles, if there's more than one, we add them together. And if one is going one way and one is going the other way, they cancel each other out. They have to be exactly going opposite ways, but they cancel each other out. Okay? If we have boron trifluoride, so these are Fs, and the middle is boron, we can see that the fluorines are quite a bit more electronegative than the boron, and I get dipoles that are pulled towards the fluorine. However, there's 3 of these. equal, and they're all equally spaced around the boron. There's no lone pairs on the boron. That keeps them equally spaced. That means this molecule is also nonpolar. And the last one is carbon tetrafluoride. We have carbon in the middle and fluorines on the outside. Again, the fluorine is much more electronegative than the carbon, so we have electrons in those bonds pulled toward the fluorine. And there's 4 of them, except they're equally spaced around that carbon. So if I add them all up, they cancel each other out. So if I've got atoms or molecules that are linear, trigonoplanar, or tetrahedral that don't have lone pairs on them and have all the same polar bonds, the molecules aren't polar because the dipoles cancel out. Now, for a molecule to be polar, then, it's kind of everything else. So, if the molecule only has one polar bond, then it's polar. An example of this is this CH3Cl. The carbon-hydrogen bonds aren't polar, and the carbon-chlorine bond is. Chlorine is more electronegative than carbon, so those pair of electrons get pulled toward the chlorine. Overall, there's not another dipole to cancel that one. So that molecule is polar. Okay. Formaldehyde, the same thing. We have a dipole along the carbon-oxygen bond because that's polar. The carbon-hydrogen bonds aren't polar, so we get this overall dipole going towards the oxygen. Again, there's nothing canceling that, so that's a polar molecule. Okay. The second one is the molecule contains polar bonds and the central atom contains non-bonding electrons. So, for example, water. So water has hydrogen, oxygen, hydrogen. There's 2 polar bonds, with the electrons getting pulled towards the oxygen, because oxygen is more electronegative than hydrogen. And 2 lone pairs are non-bonding pairs. Okay. Right now, it looks like they cancel out, but that's not. Water's not linear, right? If it's got 4 electron groups around it, the electron group geometry is tetrahedral. So if I look at that, oxygen, hydrogen, hydrogen, lone pair over here, and a lone pair up here. Okay, so water's bent, so the dipoles don't cancel out. So if I've got a molecule that has polar bonds, but I have a lone pair or 2 lone pairs on the central atom, the molecule is going to be polar. Okay? And the last possibility is if I've got polar bonds and they're not all the same. For example, this is carbon with 2 chlorines and 2 fluorines. So carbon dichloride, difluoride. And the chlorine atoms aren't as electronegative as the fluorines. So what I get are these, I'm going to draw them big, because the fluorines are more electronegative than the chlorines, and I'm going to draw these small. All the bonds are polar, except the carbon-fluorine bonds are much more polar than the carbon-chlorine bonds, so they don't cancel each other out. Okay, so that molecule would be polar. If we take a quick closer look at water, water we saw has 2 lone pairs, or 2 non-bonding pairs on the oxygen, and 2 bonds to hydrogens. The oxygen is more electronegative than the hydrogen, so we've got these dipoles in this direction. What happens if we add those together? We get an overall dipole that's pointing straight up through the oxygen. So that means the oxygen is going to end up being slightly negative, which we see, and each of the hydrogens are going to be slightly positively charged. Overall, if we look at an electron density map, we see up here there's more negative charge, and down here there's more positive charge. So on the oxygen there's more negative because the electrons spend more time there, and the hydrogens are more positive because the electrons are being pulled away from them. Alright, so that's how we assign if molecules are polar or not.